In the last class, we have derived the very important Km equations. So the Km equations have two sets of Km equations, one for displacements. So d is an analytic function containing the displacements. So d is, if you remember, u plus iv, where u is the x displacement, v is the y displacement. And the task of finding these functions u and v all over the body is reduced to the problem of finding two analytic functions, capital omega z and small omega z. Similarly, for the stress equations, which are here, these are the Km stress equations. The stresses, the three stress components, sigma xx, sigma yy, and sigma xy, are again derived in terms of these two analytic potentials, capital omega z and small omega z. So if you can find these potentials somehow, then you can get the stresses as well as the displacements without solving any partial differential equation, and sometimes by just arguments rather than lengthy calculations. How do we find these potentials? Most of the time, the key to finding these equations is to use boundary conditions. So as you are aware, elasticity problems have two kinds of boundary conditions. Some parts of the boundary have displacement boundary conditions. That means displacement are specified on certain parts of the boundary and tractions are specified on other parts of the boundary. So we have talked about the boundary conditions. When tractions are specified, this is how the boundary condition is written as. So on the part of the boundary del omega t where tractions are specified, I times this quantity is the total force that is applied on the boundary. This is the total force. These are specified tractions. T star and T x star and T y star are specified tractions. Integrated over the part of the boundary where they're applied gives you the total force. And I times the total force is equal to hz evaluated at S2 minus hz evaluated at S1, where hz is actually this function with alpha equal to 1. It is again a function of, again, a combination of these two potentials that we are supposed to find. So Tx star and Ty star are known functions, and from Tx star and Ty star, from the connection between Tx star and Ty star with these potentials, we get a clue about what these potentials might be like. Similarly, if you have displacement boundary conditions specified, then 2 mu times the specified displacement is equal to minus hz with alpha equal to 4 nu minus 3. Hz is the same function. Alpha is 4 nu minus 3 in case of the displacement boundary conditions, and equal to 1 in case of traction boundary conditions. Again, if you have the displacements known, if these are known displacements, then from the connection between these displacements and these functions, you get a clue about what these functions are like. Once you have got that, you put them back into the Km equations and see whether the Km equations make sense. And if they do, then you have found the solution. We also need to sometimes look at these Km equations in cylindrical polar coordinates. We have derived that as well. And in cylindrical polar coordinates, the stresses are sigma rr and sigma theta theta. The first Km equation in terms of sigma rr plus sigma theta theta remains unchanged. It's the same as in the Cartesian system. The second equation is also same except for e to the power 2i theta here that you need to apply. So the second Km equation is written in terms of sigma rr minus sigma theta theta in terms of these two Km potentials with e to the power minus 2i theta added to the equations. So these are the Km equations in cylindrical polar coordinate system. The displacement boundary conditions are these. So again, e to the power minus I theta comes about because you are changing now the displacement components to r and theta system rather than x and y system, and these are these are the traction boundary conditions in the cylindrical polar coordinate system. Now, with all this and what we have learned about complex variable theory, especially contour integrations, residual theorems, and so on, you have to remember those results in order to appreciate the next few problems that we are going to do. This week, we will do problems of different kinds, which will lead up to problems involving cracks. Uh, we will we will just scratch the surface of crack problems at the end of this week, and then next week we will go deeper into different kinds of crack problems that we will solve with what we have learned in complex variable theory and the KM equations.